In this video, we are going to be talking about chapter 9. And chapter 9 is on systems of equations and inequalities. So, let's write this down here. So this chapter is on systems of equations and inequalities, but in particular, it's a chapter on matrices. So the goal is that we're trying to solve a system by using matrices instead, right? So we know how to solve systems so far. We've talked about elimination and substitution as two methods that we are able to use to solve a system. Now what we're going to do is we're going to try and use matrices to solve these systems instead and see how these might be more systematically solved when the dimensions are higher, right? So right now, if you have like a system with two equations, that's not that difficult, right? You can do substitution or elimination for a system with two equations without much effort. But what happens when there's three equations or four or five equations? We haven't really solved those, but they are difficult to do, right? So the goal is, like I said, we want to use matrices to solve these systems. So really this should be chapter 9 matrices, but it is not. Okay. So let's start with this. A matrix itself, let's define what we're working with here. So a matrix is simply a rectangular array of numbers. Okay, so a matrix is a rectangular array of numbers, and our goal is going to be somehow to manipulate this matrix using what we know about arithmetic, right? Now, it is this array of numbers, but it is also arranged in rows and columns. Okay, so a matrix is a rectangular array of numbers, and it's arranged in rows and in columns. Not only that, a matrix has entries. Okay, so a matrix has entries, and these entries are just the numbers in the array. Okay, our matrix will have some dimension or sometimes we call it order. In this class, we won't really focus on order. We'll talk about it as the dimensions of the matrix, but the dimension is just going to be the size of the matrix. And generally, this is written as m by n, where m is always the number of rows and n is always the number of columns. So when you define the dimension, when you talk about a matrix, you always say rows by columns. So rows is always, always, always first. Rows by columns. Okay. So in this example, right, let's put something here. Let's say I have some matrix A. Usually we define matrices as these capital letters. So you'll say matrix A, you'll put a capital A. We will talk about the entries and things like that, little a's. So you don't really use small lowercase letters when you're talking about matrices. So A might be something like 2, -1, 0, 4, 3, 5. So let's say this is my matrix. Note that this is some rectangular array. It's got 2 rows and it's got 3 columns. So it's kind of like a grid. So I'd say, okay, well, the dimensions of this matrix is a 2 by 3. So 2 rows, 3 columns. This matrix itself is, I would say, not a square matrix, right? So A is not a square matrix. A square matrix would be when the rows and columns are the same. So this would be like a 2 by 2 or a 3 by 3. This is a 2 by 3, not square, right? But if I were to just, for example, delete, let's say this column, that would be a 2 by 2. That's a square matrix, yeah? So this one's not a square matrix. And I can also define the entries like I was talking about with a lowercase letter. So generally, if this is capital A, I could define different entries by using, I'll put it over here. So my entries will be A sub ij usually, where I is the number of rows, j number of columns, right? So as you'd expect, right? So number of rows, number of columns. If I choose, for example, this 3, this would be the entry A, 2, 2, because it is the entry in the second row, second column. If I chose, let's say, this one here, this would be A13 because it is the first row, third column. So it's A13. So we will define our entries with this lowercase, and we'll always, again, row by column, rows first, column second. Okay. Okay. Hopefully that is making sense. So let's do another one. Yeah. So let's say I have matrix B, which is a 1, 7, -2, 0, 5, and 3. We have this matrix. This is, note here, a 3 by 2 matrix. And the question might ask me to figure out what is, right? So like find B31. Yeah. So it'll ask me for something like this. So B31, what would B31 be? Well, B31 would be row 3, column 1. Row 3, column 1 would be 5. Okay. Row 3, column 1, we got 5. So again, maybe it's asking us something like that. Maybe it's asking the dimension. It doesn't really matter. Yeah. You could just hold different values. So I think that's pretty self-explanatory, finding these entries, things like that. We won't really do much more on this. But the next thing we'll talk about is what I am going to refer to as an augmented matrix. So an augmented matrix is going to be the matrix that gets formed by listing my coefficients of my variables, and then it's going to be followed by a vertical bar, and then the constants of your system on the right hand side. All right, so when I write this out, this will kind of make more sense. But basically, you're gonna take a system. So I'll do an example here. Let's say 2x 3y equals 7. That's my system. And x minus 4y equals -1. So this is my system, right? It's got this first equation, the second equation. These are making up my system. And what I want to do is I want to create the augmented matrix from this system. The augmented matrix looks like this. It looks like 2, 3, 1, -4. So these are the coefficients. Maybe 2, 3, 1, -4. So that's what this is, right? We take the coefficients, and then we do our vertical bar, and then we put our constants 7 and -1, which is the right hand side, right? So we see over here 7, -1, 7, -1. So we create this augmented matrix where we have the coefficients, the variables over here, and then we have this vertical bar, and then we put the constants over here. Now we're going to come back to this augmented matrix in a bit, but for now, we're just kind of learning how to set up the augmented matrix, and it's basically move kind of back and forth between augmented matrix and the system and vice versa, okay? Remember, keep in mind, the entire goal of this chapter is for us to use matrices to solve systems. So we are right now turning a system, converting it to its matrix form, right? We're using an augmented matrix, which is basically taking the system and creating it into a different form, and that is the form of a matrix to use and solve. Okay? So focus on the end goal, right? Always keep this in mind. We are trying to use matrices to solve the system of equations that we're given. All right. Okay, so let's now talk about a couple things involving matrices. And first, it'll be the equality of matrices. So we've seen with matrices, remember that we have these different entries, right? So each position has some row and column designation corresponding to that value. And for two matrices to be equal, so if you're trying to prove A equals B, right? Matrix A equals matrix B, this would only happen provided that A sub ij would equal B sub ij for every position, right? So every entry would have to be the same if the matrices are going to be the same. Pretty self-explanatory, right? The corresponding matrices, the corresponding entries of the matrix all have to be equal for the matrices to be equal. Note that there is kind of this caveat here where A and B must have the same dimensions, right? So you wouldn't be able to set the two entries of matrices together unless they were the same dimensions, because one of them would have an entry and one of them wouldn't. There's no way for those to be equal. Yeah. So it's inherent that if you're trying to find if two matrices are equal or not, that one, they are the same size, right? Same dimensions. And then two, that every entry is going to be equivalent as we go. Okay. So let's try an example. Let's say I have these two matrices. I have x plus 1, 4, 0, and 2z. And I'm trying to see if that's equal to 6, 4, 0, and y minus 3. Now here that some of these entries are not constants anymore. They have variables in them. And so if I'm trying to show that these two are equal, right? If I'm saying that these matrices are equal, I would want to find the variables that make those matrices equal. Yeah, so I have some x, some y, and some z value. I would love to determine what x, y, and z are to guarantee that these matrices are going to be equal to one another. In order for this to be true, like we said, every entry has to be equal because these are 2 by 2s. So this is a 2 by 2, this is a 2 by 2. I know at least they're the same dimensions, so I can start to compare. I would say x plus 1 has to equal 6, right? Row 1, column 1, and row 1, column 1 have to be the same. 4 is equal to 4, so that's great. 0 and 0 are also equal. That's great. I also would need to prove then that 2z equals y minus 3. Yep. So I can solve for x. It's 5. This one here is a little bit trickier. So what we find is that whichever way you want to do this, I might find y is 2z plus 3 or 3 plus 2z, right? So all I did was add the 3 to the other side. If this is true, right, what you do is that means one variable can be essentially whatever you want, right? Like z, you can make z some term and it won't impact the problem, right? Like as long as you choose a z, the y is going to be changed corresponding to z, so you can let z be anything. So z is technically like a free variable in that we can choose whatever we want for z, and then the y will just match it. Similarly, if you solve for z here, then in that case, the y would have been the free variable, right? Because z would be dependent on y, and so y could be whatever you want. So in this situation, this would be true. How you would do this is you would write something like this. You would say the solution here would be something like x equals 5, y equals 2t plus 3, and z would equal t. So basically what I do is I create a new variable, right? Obviously different than the X, Y, and Z you're using, the ones that are in your system. And it's going to be basically a constant. So it's not really a variable. I mean, like the T is essentially a constant that you are going to decide on. So whatever that number is, that would be over here as well. And then you get your solution. So like you'd say, okay, constant T equals 1. If T is 1, Y would be 2 plus 3, which would be 5. You get 5, 5, 1. Yeah. So Z is the free variable. You're assigning it some kind of new thing. We'll call it T, some constant. And then whatever that number is, everything will get adjusted. So this is one way you could do it. Obviously, this isn't always the case, right? You might not have a free variable. It might be like you found, X had to be 5, Y had to be 2, and Z had to be 3. If that's the case, then that's the case, right? Those are the only solutions here. Technically, with this free variable, that means we have a lot more solutions, right? There's not just one solution. We have a lot more flexibility. Okay. Okay. Now, from here, we will talk about the addition and subtraction of matrices, and we will talk about scalar multiplication of matrices. All right, so let's go ahead and do this. Let's start with addition and subtraction. So this should make a lot of sense as well, but if you're going to add or subtract, you would just do these entry by entry, right? So addition and subtraction, this will just happen entry by entry. Note again, all of these, the caveat is they have to be the same dimensions, right? If they're not the same dimensions, then there's no way to add or subtract the corresponding entries, so it wouldn't make any sense. Yeah, so they are going to have to be same dimensions. So addition and subtraction, you go entry by entry. If you want to do scalar multiplication, you will just do this by multiplying every entry by this, right? So a scalar multiplication, you just multiply every entry by that value. Yeah, so let's do a couple examples. This should make perfect sense to us. It's very straightforward. The addition and subtraction. Yeah, let's say I have matrix A, 1, -2, 3, 0. I have matrix B. It is 4, 5, -1, 2. If I want to find, let's say, A plus B, you would take matrix A, you would add to it matrix B, and you would just go entry by entry. So you would go row 1, column 1 with row 1, column 1. You would get 1 plus 4. You'd get row 1, column 2, row 1, column 2, -4 and 5. -4 and 5. That's not it. -2 and 5. My apologies. Row 2, column 1 and row 2, column 1. Same entries in both. You add those. So it's 3 plus -1. And then row 2, column 2, row 2, column 2, you get 0 and 2. So in the end, my matrix addition is 5, 3, 2, 2. 5, 3, 2, 2. Okay, so you add entry by entry. If I were to subtract, same process, right? So you take this matrix minus this. I'm not going to fill these out. We can just kind of make a copy here, right? This would be 1 minus 4, -2 minus 5, 3 minus 1, and then 0 minus 2. So in the end, you'd get what? -3, -2 minus 5, -7, 3 minus -1 would be 3 plus 1, 4, and 0 minus 2 would be -2. Okay, so that would be my subtraction. And then last but not least, we can do a scalar multiple, right? So we could do like 3a. So 3a just means, hey, scale every entry in A by 3. Yes? So you would take your A matrix and scale by 3. So it would be 3 times 1, 3, 3 times -2, -6, 3, 3, 9, 3 times 0 is 0. That would be the scalar multiplication. All right? Now, building off this, you can have some linear combination of matrices as well, which just use the properties above, right? So linear combinations, this could be something like, I'm going to use the same matrices, right? So let me write these out again. A was 1, -2, 3, and 0. And then B is going to be 4, 5, -1, 2. And then what I could do is, in this example, I could find 2a minus 3b. So it's a linear combination. Now, this is just going to do what we've seen previously. We do a scalar multiplication, and then we just subtract those two new matrices that get produced. So this would be 2a. If it helps, you can write it out. So 2a would be 2, -4, 6, 0. 3b would be 12, 15, -3, and 6, I believe, right? Would be good to check these numbers as I'm doing them. I believe these are correct, but you know how sometimes it happens. So 2 minus 12, -10, -4 minus 15 would be -19, 6 minus plus 3 would be 9, 0 minus 6 would be -6. So this should be the matrix 2a minus 3b. Okay, it'll still be this 2 by 2 because everything was 2 by 2. It's just been kind of scaled and adjusted a bit. Okay, awesome. So talked about a decent amount of things. Yeah, we talked about our matrices, how to find these entries, the dimensions, how to kind of combine some of these together with addition, subtraction, doing scalar multiplication. We even talked about augmented matrices. Yeah. Another thing that we will want to do is we will want to figure out how to multiply matrices. So right now we've only talked about adding, subtracting. What about matrix multiplication? So matrix multiplication. So with matrix multiplication, okay, let's first show A times B. A is going to be, we're going to call this an M by N matrix, okay? So it'll be M by N. And then our B matrix, we're going to call it N by P, okay? So I'm just making up some arbitrary letters here to denote the row by column values that we have. So this is an M row by N column, and this is N column, or N row by P column matrix here. The result, AB, is going to come out to be an M by P matrix. Okay. So what this means is, right, before we can show how to multiply, I'm going to show kind of the requirements. So in order to do a matrix multiplication, what you first need before anything is you need the inner dimensions to be the same, right? So I need my inner dimensions. I need these to be the same. In this case, they are N and N. These inner dimensions are the same, which means you can go ahead and do multiplication, right? So in order to get the multiplication, the product of these two matrices, you need the inner dimensions to be the same. This was true. And so if those are, then the result will be the outer dimensions. So the outer dimensions here is going to be your new shape. Okay, so A multiplied by B will produce an M by P matrix because the inner dimensions were the same N and N. All right. Hopefully that is making sense. Now, to actually do the multiplication, we need to figure that out. But first, just these caveats, right? We need to make sure that the inner dimensions are the same. And if they are, the result is the outer dimensions. I should note, very important, matrix multiplication is not commutative. What this means is that AB is generally not equal to BA. Now, that's not to say that it can't be. There are some situations where A, B, and BA are going to be equal, but in general, AB and BA are not going to be the same thing because the matrix multiplication, the way we actually perform it, is not going to be commutative like a normal multiplication would be, right? Like if you take 2 times 5 or 5 times 2 with just numbers, right? Not matrices, but numbers, that is commutative, right? You can do either or and they are the same. Matrix multiplication doesn't work like that. So keep that in mind. Yeah. Okay. So with that being said, how do I actually do the matrix multiplication? What you're going to do is you're going to multiply row by column entries. So I'm going to say to do matrix multiplication. You're going to multiply row and col entries and sum or add across the rows and columns you're in. So this is kind of a quick and dirty explanation of what it is. I'm going to show you what it actually is to make a little bit more sense. But essentially, if you want to find the entry in a location, let's say row I, column J, you would multiply the entries of row I by the corresponding entries of column J in each corresponding matrix, right? And then you'd add the results. So let's do an example, make sense of this. Let's say that I have a matrix that is 1, 2, 3, -1, and I'm multiplying by another matrix, which is 4, 0, 2, 5. Okay. first thing I want to note, this is a 2 by 2. This is a 2 by 2. So the inner dimensions agree. I can do the multiplication, and therefore the outer dimensions tell me the new shape. My new shape is a 2 by 2. So I will make a matrix with 2 rows and 2 columns. It is a 2 by 2, right? Now, to do the multiplication, right, you take row by column, right? This is the general sentiment, right? Row by column. So what I'm gonna do is I'm gonna take, if I want to find this entry will be what I call A11. That is the entry in row 1, column 1. If you want entry 1, 1, you will therefore take row 1 and column 1, row 1 of the first matrix, column 1 of the second matrix. You will go ahead and multiply the terms that correspond, and then you will add them. So what that means is if I'm doing row 1, column 1, yes, I will take my row 1, column 1 entry, multiply it by my row 1, column 1. So I will take the first term in this row, and I will multiply it by the first term in this column. That would give me 1 times 4. And then I will take the second entry and the second entry, right? Second entry in that row, second entry in that column. And I will then multiply those. And then I will add those together, right? So you were going row by column, and you will take entry by entry, and you are going to be multiplying these and then adding them together. So I look at row 1, column 1. I take the first term times the first term, and then I add it to the second term times the second term. If there were more, you would do third term and third term multiplied, add that, fourth term, fourth term multiplied, add that, and so on and so forth, right? Then I would repeat the process. I would go to A1, 2. So row 1, column 2, row 1, column 2. So you will look at row 1, column 2. So if I do row 1, column 2, row 1, column 2 will look like this. Row 1 will be 1 times 0, 2 times 5. I add those together, right? First entry, plus second entry times second entry. 1 times 0 plus 2 times 5. And I will repeat this process again. So let me do A21 and A22. A21 and A22. So for A21, I'm just going to fill these in, okay? So A21, I'm going to take second row, first column. So again, we're not going to be able to highlight all these every single time, obviously, because you're going to need to get your final output, and you can't rewrite the matrix like 20 times to show each one, right? So row 2, column 1 would be something like this. Row 2, column 1, 3 and 1, or sorry, 3 and 4, and then -1 and 2, and then you add those together. Row 2, 2, or entry 2, 2 would be row 2, column 2, so that's 3 and 0, -1 and 5. 3 and 0, -1 and 5. Okay. Okay, so great. What is that going to be? Well, our matrix multiplication comes out to be this. 4 and 4, 8, 0 and 10, 10, 12 and -2, 10, 0, and make sure this is right, -1 and 5, yep, -5. So it'd be 8, 10, 10, -5. That is our matrix multiplication. Okay, again, remember, we're going kind of row by column, and we're doing the corresponding entries, right? First entry, second, third. We multiply those, we take the product, and then you sum the values. Okay. Hopefully this is making some sense. I'm going to do another example. So let's think about this same process. I'll leave this in view so we can kind of look at that again to try and make sense. So in this example, I'm going to take a matrix that is 2, -1, 3, 0, 4, 1. And I'm going to multiply it by 1, 2, 0, -3, 5, 1. So first and foremost, you need to check that you can actually multiply these, right? I may give you some multiplication written out like this, and it turns out that the dimensions actually don't match up, and you can't do the multiplication, yeah? So you're going to look at this and you're going to say, okay, can I do the multiplication? And I'm going to check it by looking at my dimensions. This is a 2 by 3, 2 rows, 3 columns. This is then a 3 row, 2 column. This is a 3 by 2. So what we see is that the inner dimensions match. This is 3 and 3. Awesome. And then it will produce something of size the outer dimensions, which is a 2 by 2. So this is going to produce a 2 by 2. I'm just going to leave these kind of placeholders here, these underlines, so we can see what we're filling in, right? But I know it's a 2 by 2, so I create something that has like 2 rows, 2 columns in shape. And then let me go ahead and quickly compute these, yeah? So this entry would be 1, 1, which means I want to take row 1, column 1. So I would do 2 times 1, -1 times 0, 3 times 5, and I add those up. So that's going to be 2 and 15, which is 17. This is row 1, column 2. So you'd take row 1, column 2, and I'd go through that. This would be 2 and 2, 4, -1, -3 would be 3, 3 and 1 would be 3. So that is 4, 3 and 3. 4, 3 is 7, and then the 3 is 10. Then I would do row 2, column 1. That's this entry here, row 2, column 1. So I would take row 2, column 1, which will be 0, 0, and 5. So you get 5. And then row 2, column 2, you'll take row 2, take column 2. 0 and 2 is 0, 4 and -3 is -12, 1 and 1 is 1, -12 plus 1 is -11. This would be my matrix multiplication. Okay. So hopefully, again, this is making some sense. We're doing our multiplication. We're going to be checking the entry, seeing the row and the column that we want from each matrix. We will multiply the entries as we go through, across the row or down the column, and then we will sum the products, right? So it's kind of like a sum of those products. Okay. Okay. So matrix multiplication done. The other thing we'll want to look at in 9.4 is, so I should have noted all the way up above, right? We were in chapter 9. I never kind of labeled the first part. We were in technically 9.4, which is just the algebra of matrices. So maybe I add this here, 9.4, the algebra of matrices. Not really that important, but just making sure who we know where we are. So all of this was kind of 9.4. And now we're going to shift the gears a little bit. We're not going to shift gears. I'm going to talk about 9.5 in just a moment, but the last little piece in 9.4 I want to add is writing a linear system as a matrix equation. Matrix equation. Okay, so I want to write a linear system as a matrix equation. So what I'm going to do is I'm going to create my linear system. So I'm going to use the same system we did last time. I'm pretty sure 2x 3y equals 7, and then x minus 4y equals -1. What I want to do is I want to create the matrix equation where the matrix equation looks like this. It looks like ax equals b. Okay, so this matrix equation is going to kind of have this form, ax equals b. And the a is the coefficients. So we call this like the coefficient matrix. The x is the variables. So it's the variable matrix, we call it. And b is what we call the constant matrix because it contains all of the constants. So it's kind of similar to what we do with the augmented matrix, right? Where we had like the coefficients on the left side and then we have the constants on the right side. Very, very, very similar process. So if I wanted to create the matrix equation of this, what would that be? Well, this would get converted into, so remember, I want A, so AX equals B. So AX equals B. A is the coefficient matrix, so you take the coefficients, which is 2, 3, 1, -4. I take the variable matrix, which is just x and y, right? We have x and y in the problem. And then I take my constant 7, -1. Note that these are kind of shaped this way. For example, like the variable matrix xy, it's not a horizontal, it's a vertical matrix. We call it like a vector. This is a column vector just because it's one dimensional. Same thing with like a row vector. It would be a matrix that has like one dimension. We call it a vector. Nonetheless, though, XY, you see it's 2 rows, 1 column. It's only 1 column because the matrix multiplication requires that. Yeah. So if you did the matrix multiplication here and you did row by column, you do this row by this column, it would be 2 times x plus 3 times y. Well, look at that, equals 7. So it works out like they're made to be this shape. If you set this up and you recognize that the shapes don't match up for a multiplication, right? Like your inner dimensions aren't matching up and all that. You'll know to make the switch. But ax equals b is what we're getting at. This is my matrix equation. Okay. Again, we haven't talked about what to do with these yet. Yeah, our goal is eventually to discuss what we're going to do with these. But for now, we are just creating the matrix equation itself. Let's do this again, but for a higher dimension. So it doesn't always have to be a 2 by 2. Yeah, we can have a 3 by 3, 4 by 4, 5 by 5. It can go on higher and higher. So let's assume I've got this system. X minus 2y plus z equals 4. 3x plus 2z equals -1. 2x plus y minus z equals 0. And I want to go ahead and convert this into its matrix equation. So what will this be? Well, let's go do this. It'll be ax equals b. So A, note that there are 3 equations and 3 variables, which means that A will need to be a 3 by 3 to account for all the locations, right? So 1, -2, 1, 3, 0, 2, 2, 1, -1. We just take the coefficients of all these all the way across. Multiply that by the variable matrix x, y, z, and that should equal the constant matrix, which is 4, -1, 2. So this is A, this is X, this is B. Okay. Okay. Hopefully this is looking good to everyone. Yeah, we're creating this matrix equation. We're gonna obviously use this matrix equation form to solve our system soon, but for now we just need to create the matrix and understand its matrix equation form. I will note that we have a couple pieces here that we will want to talk about. And essentially, this is categorizing our systems. So our systems can be of two forms, I suppose, two categories. You can either have a system that is consistent, and some of us might remember this from 1033, right? We talked about consistent, inconsistent as well. But for a system to be consistent, that means that the system has a solution. So that could be more than one, right? So it could be greater than 1. So infinity as well counts, right? So as long as you have a solution, you can be considered a consistent system. You would be inconsistent. I'll take a guess. You would be inconsistent if your system has no solutions. So system has no solutions. All right. Now, when would this happen? Well, this you can kind of see very obviously. So you would have no solutions when you would have some row that was a bunch of zeros. And then on the right side, you have some constant, right? So in the example, I had like a bunch of zeros. And then on the right side, the constant was a 1. This means that no matter what you plug in for X, Y, Z, whatever it is on the left side, there would be no way for you to be able to get that equal to 1. So no solution, right? There's no values you could plug in to make it equal 1 or whatever. I put 1, but it could be 5, it could be 3/2, it could be whatever. So there's no numbers to put that in. So if you know that the left side has all zeros and the right side has some number, you would have no solution. That would be inconsistent for your system. All right, so keep this in mind. There is a little bit on the homework talking about consistent versus inconsistent systems. I want to make sure we all feel comfortable kind of solving those.